Sorry, just getting the Zoom meeting ready. Tomorrow, or it'll either be their drop grade or their excused grade, depending on the situation. So for those people, or so that way, even though those people had extenuating circumstances, I want y'all to, of course, be able to have your quizzes back before the exam. So that's my big goal for the quizzes. How did y'all feel about your first quiz? You could maybe just do thumbs up or this way or that way. Oh my gosh, that's a lot of thumbs up and sidewayses. That's good. That's great. So I think there was a lot of anxiety, a lot of people coming to my office today, even though I didn't have office hours, because of that first quiz terror. But I do try to be very open about what's on the quiz, and I don't do it to trip you up. I really do it for you to have the opportunity to practice taking assessments and also to have accountability for you to study as we go instead of smushing it all right for the exam. So they're not usually going to be too difficult. I try to make them accessible to where we're at and what you should have practiced. So like the resonance question wasn't too crazy hard because we haven't spent a lot of time on resonance yet, that kind of thing. Okay, any thoughts on the quiz? Was there anything that helped you study well? Anything that you want to, not about the content directly, but any questions you have about the structure or anything like that? Okay, yeah. Just like one sheet or one card. I don't want you to use it as a crutch, which is actually sometimes when you have open notes, students don't study. In the summer, that's not as big of a problem because everyone's like so terrified of how fast the class is going anyway, but I don't want you to use it as an excuse not to study. I want you to use it as a tool for things you didn't have time to memorize yet, basically, because it's so fast paced. So it just kind of helps like a little extra so that you don't have to have everything in your brain, but you should be able to perform the materials well, if that makes sense. So, and it kind of helps also give accountability for you to study and make your own study guide, because then you can use it on the quiz. So that's what the goal of that is. So I don't want you to have all your notes. I want you to be able to condense your notes, make concept maps, and recognize where your shortcomings are. And I want you to bring that with you to the quiz, if that makes sense. Did you have a question? No note cards for the exam. If there's something that I'm like, oh, they haven't had time to memorize this yet, like on this upcoming exam, there might be some PKA stuff. If there is, I'll give you a PKA table. So I'll give you something if I feel like you need it. But I want you to have solidified most of the information in your brain by the time we get to that point. Yes. I like to do bonus questions, partially because I feel like it gives you an opportunity to show if you've gained a deeper understanding. So they usually are like maybe a little bit more difficult. Like not very many of us have practiced creating resonance structures yet because we only learned about it yesterday. So that was part of why I put a more challenging one there. So it's almost like a challenge question. And then also I like to give y'all every opportunity to make your grade better. So that's part of it too. So I try to always do a bonus question. Any other questions? Okay, great. So here are some reminders. My office hours are Tuesday, Thursday. A lot of people came today and it broke I was like, yay, y'all are coming to office hours, but not when I have them. And it made me so sad to turn you away, but I really have to protect the time I have to prepare for class and to make sure I have everything in order before class, because that's really important for me. And some days, if I have a lot of requests, I will open up office hours on a Monday or a Wednesday if I have a lot of requests or whatever. But today I had a doctor appointment, so I absolutely needed the 1 hour before class to do that. So that's why I didn't turn you away, because I didn't like you and I really wanted to keep you. After you left, I was like, oh, I hate doing that. I wish I could have brought them all in and just chatted with them for an hour, but I couldn't. So that's when my office hours officially are. And also when I went to my doctor appointment today, it was a gastroenterologist and she came in and was like, I hear you're a chemistry teacher. And I said, yeah, I am. And she said, I was a chemistry major. I love science. And she got really excited. And I told her I'm teaching 5 weeks 1. And it's like so fast paced and I'm stressed out for my students. And she said, I took ochem in summer 1 and it was all so crazy. And now she's a doctor. So all of you who are taking this now and want to be doctors, I thought that was kind of a fun connection for you. She was really nice. So I'll get your quiz back to you by tomorrow at the latest. I'm going to do a video key, but again, I'm not going to post that until everyone's taken it. So don't expect to see it before class tomorrow. Your homework is due Friday. So that's not a day we have class. It's due by the end of the day Friday, just to give you an extra day to work on things and catch up. And what I want to see on that is whatever kind of documents you want to do it on. I don't care. All the questions for the practice problems for chapter 1, all the practice problems for chapter 2, and whatever point we get to for chapter 3. So I don't ever grade you on things that we have not talked about in class yet. So if you're ever stressed, like, is this going to be on here, even though we didn't finish chapter 3, I never expect that. So I don't want you to worry too much about that. So it's chapter 3 up to what we've covered. And then the first exam is, again, it's Monday and it'll be from 1 to whatever we get through in 3 this week. So it might not be all of chapter 3. It might be all of chapter 3. I'm not going to test you beyond what we cover at the end of the day on Thursday. Okay, so I did have a doctor appointment this morning. I have to have a procedure done on Monday. It'll be a colonoscopy. It'll be brutal. Not excited, but that's when your exam is. So I'm not going to be here, and my wonderful colleague, Dr. Corrales, will be here. I really love them. They're amazing. Their pronouns are they, them. So try to be respectful and use the right pronouns. And they're doing me a big favor by coming here and proctoring your exam. So, but they also teach ochem. And they know a lot. So if you need a clarifying question, they'll be able to help you with that. And then I am going to record class ahead of time. So your exam's only 50 minutes, and then we have another 50 minutes of class, right? So you can leave after your exam, but then go home and watch what I recorded online. So I'm going to ahead of time record like a lecture for you and post it. It won't be material that's on the exam. You can watch it after your exam, but you are responsible for watching that, even though I'm not lecturing in person, because we can't afford to miss that 50 minutes. There is no other day of the week I could make this happen. I tried really hard, but they only do this procedure on Monday and Tuesday. And if it was on Tuesday, I was going to have to miss 2 days. So, so sorry that I'm missing your first exam. I hate to not be here with you for that. I'll also post test taking tips before the day of. Yes.
If we have to be in here from like, I suppose, like 11 to 11:15 for the exam, can whoever's coming in, can they just play the lecture up there, so like,
they have a meeting at noon, so they have to leave right when the proctor is done, but anyone can log in on here. Like, this screen is just open, so any one of you can use your UNT ID. That's a great idea, and play the recording in here on Zoom. So you can, I think I am going to post it on Zoom, because Zoom lets you switch back and forth between the screen and my webcam, or like my document camera. YouTube doesn't do that very well. So it'll be a Zoom recording that I post, just like all the other class recordings are posted. So if you log into, you don't have to do Zoom. If you log into myunt.edu, there will be the link there, and you can just click it and it should play up here if you want to. That's a good idea. And then y'all can all talk about it. Yeah, I love that. And I don't think that there's anything happening after this class. Sometimes I'll have to leave right after, like today I have a meeting right after this, but y'all are welcome to stay and do like study groups and talk about what we've learned. I think that's a really good idea until another professor comes in and kicks you out. But I think at least for an hour after our class, no one's here, because I was in here for an hour yesterday and nothing happened. So you can use this space. You're welcome to do that. Just be respectful. Okay. So when I'm not available, I try to be as much as I can. But when I'm not, please talk to each other. A lot of you know one thing and somebody else knows the other thing, and then you can come together and teach each other. It's really, really helpful. I want you to use each other as a resource, not just in this class, but every class you're in, use the people around you. And the Chemistry Resource Center is on the 2nd floor. Don't forget about that. The Tutoring Center has tutors available who teach ochem as well, the UNT Tutoring Center, and you can, I think, get tutoring for free through them. You can always look at my videos. The Organic Chemistry Tutor YouTube and Leah for Sci YouTube are some of the best resources that I know of. And then also on the resources, like extra resources, there's some documents that I think are really helpful that you can look at. A lot of times when people come to me and ask me a question, the very first thing I'll say is, did you watch the video on it? Because that's part of why I make those videos, is because they're questions that get asked a lot. So if you have a question, that's your first resource, so that I can do as much on the back end and make more resources for you, and I'm not answering the same question over and over. That's part of why I make all those videos. And if you have a request for a specific video that I haven't done yet, I want to hear it. So email me and let me know, or tell me. A lot of those videos came to be because students would be asking for them. Okay, before we get into this stuff, I do want to do a few other things. So resonance is one of the hardest, it's not hard to understand. I think the idea that it's an average is like, oh yeah, we get that. Neither of these structures exist. What is hard for students typically is drawing resonance structures themselves, knowing like, is this a good resonance structure or not? That's been consistent for me throughout, and resonance doesn't go away. It plays into every single chapter pretty much. There's like maybe 3 chapters where it's not a key feature, but it stays in ochem, and it stays in ochem 2 in an even bigger way. So resonance is not going to go away. There are some things that you might get away with not understanding very well, because we talk about it at the beginning as a foundation, like visualizing hybrid orbitals. You probably don't need to do that a ton. You do need to do resonance a ton. So I really want to encourage you. I took a chapter out of the Klein Organic Chemistry, the Second Language. So it's not really a textbook. It's like a handbook of practice problems. And I did that for 2 reasons. One, because I don't have time to go through step-by-step resonance questions with you the way I want to, and this book does that. And 2, because I wanted you to have an example of what this book does, because I think it can really, really help students. So I wanted you to check it out. So this is chapter 2 about resonance, and what you can see, they kind of do a very brief overview, and it's not like textbook language where you're kind of like, I'm annoyed by how much this is talking about things I don't understand. Like, it's very, very clear. There are things like bad arrow instead of like, this doesn't work because of whatever. Like they explain it in like everyday language terms, which I like. So like, for example, they have 2 commandments that you can focus on. You're not going to break a single bond. I would change that to a sigma bond, because you are going to break bonds, but not sigma bonds. Single bond makes it seem like you'll never break any bond at all, but you will break a double bond, right, to make it a single. And then you shall not exceed an octet for second row elements. And then they have you look at examples of what those actually mean, and then you get to recreate it. And then they're like, now what's a good arrow? And here's how you do good arrows. And then they have you recreate it, right? So they have like, this is called scaffolding, where you learn a little bit and you have guided practice. You learn a little bit more, you have guided practice. And then by the end, you're making your own resonance structures. And yeah, so it's just really helpful. And at the end, I've also included the answer key. So there is a lot of examples, and there's also the right answer drawn out for you at the end. So I really encourage you to use this resource. You don't have to do all however many examples. You could do like 2 or 3 from each one to get the idea and optimize time, and be like, okay, I think I get this, I get this, I get this, and just do a few practice problems from each section to build your foundation of resonance. But I really, really want you to practice resonance. That's really important, and I can promise you that there will be a free response question on your exam about resonance. So I want you to learn resonance. It's very important for your foundation in this class, and to understand like stability of things as we go through. And there's a lot of resonance, like in every single chapter. So please do this. And then after you've done that, if you guys are still like, I'm having a hard time, I think this explains it better than I would be able to in a video, but I can try to make a video. But I honestly think the thing that people have to do for resonance is do it. So I really like that this makes you do it, and it builds you up to it. Okay, so I really want you to do that. And also, hopefully I didn't overwhelm you. I put a lot of announcements out with videos that I selected that I thought specifically would help you for this quiz. And I'll do that also before the exams. quizzes and exams, I'll be like, this will help, this will help. After class, I'm gonna say, oh, this is a good review of what we've done in class today, as much as I possibly can, because I just don't get very much time with you. So I use my videos as a way to get extra time with you and like sum up information. But there's also tips on how to take the quiz or how to study for the quiz, and I'll do exam tips and stuff that same way. So if you have any questions, I may not be able to answer them in class in person, but please pay attention to those videos I post. Check those announcements, because that's my #1 way to communicate with you, and I give you any extra information that I'm like, this is really important and I want you to have it. Because, you know, I'm busy, so if I take time to do something, it's because I really think you all need it. I really want to help you out. Okay, I think that's it as far as administrative things. Any questions? Are you sure? No questions? Okay. Well, I have a question for y'all. What on earth have we learned in this class so far? I'm going to make us a little study guide that I'm going to make you make for me, and I'll just be the scribe. So, what have we learned in this class so far? Oh, no, do I have no printer paper? What a nightmare. I have no printer paper. Well, here's the back of this blank thing. What have we learned in class so far? Lewis structures. What are some key things about Lewis structures? Sorry that you can see through this. It's kind of icky, but I left my printer paper. Valence electrons, what about them? You don't have to be the only one who answers. Everyone can answer. Formal charge, who said that? Okay, so we learned the big thing was Lewis structures. And we care a lot about valence electrons within that. How many valence electrons do there have to be? 8. And we also learned about formal charge. Now, are formal charge and the full octet synonymous? No, you can have full octets that are charged, and you can have not full octets that are neutral. Can you ever exceed the octet? Not in first and second row elements. The only one that we'll work with consistently that might exceed the octet is sulfur. But for the most part, we don't mess with those, right? Okay, what else have we learned? Great, hybridization of orbitals. And what's our big takeaway from that? Anyone can answer, or you can. What is hybridization of orbitals? How does it play into our chemistry understanding? What'd you say? They deal with the shape of the molecule. What'd you say? This determines shapes. And I like that you said overlap of orbitals, but I'm going to say overlap of orbitals makes bonds. Okay, so let's go back to this determined shape. I didn't finish writing that, did I? I'm a bad scribe. What shape is what hybridization? That's right, sp3 is tetrahedral. I'm actually going to put it off to this side. sp3, I wrote sb3. One thing you learn about me is my mouth and brain are not always functioning at the same speed. And my handwriting is terrible when I'm writing on the board, and I always make little mistakes like that. So if I'm ever confusing, please correct me. sp3 is tetrahedral. That's that weird one where 1 points up and 3 points down. Okay, what else? I heard a proper shape, and I didn't hear the orbital that went with it. So say it loud and proud. Who said that? Trigonal planar. What's the hybridization? sp2 is trigonal planar. Okay. Great. What else? Linear sp. Great. sp is linear. That's right. And how many sigma bonds is there in an sp, around an sp atom, hybridized atom? There's 1 sigma bond on each side or 2, and that makes it linear. So if there's carbon with a bond on each side, sigma bond on each side, that would be linear. Usually there's a few pi bonds around it to make that happen. Sometimes it looks like this, but there needs to be a sigma bond on each side to make that work. Okay, what about sp2? How many sigma bonds are around that? 3. So usually it's flat like this, maybe with a carbocation, or maybe with a carbonyl group or something like that, but 3 sigma bonds around it to make sp2. And what about for sp3? 4. So they have to all be sigma bonds. There's no multiple bonds at an sp4. So, and then why did I draw this wedge and this dash? One's pointing out of the page towards us, and one's pointing like back into the whiteboard, and then the 2 straight lines are in the plane of the page. Great, awesome. What else have we learned? Yes. That's a great question. Both. So if one of them is a lone pair, lone pairs will do whatever makes them the most stable. For right now, mostly that's going to mean they're hybridized. When you get into chapter 14, you'll learn about aromatic rings and more complex resonance structures. And don't call me a liar, but then sometimes they go into p orbitals, but not for ochem 1. So just put them in the hybrid orbital now. So sp3 hybridized if there's a lone pair. So what that means is the electron domain is called tetrahedral, but the shape of the molecule is called trigonal pyramidal, where it's like missing that lone pair, you can't actually see it. So that's more of a Gen Chem concept. I will probably never ask you that. But it does come into play like with water. Today I was getting ready to come here and my modeling kit was in my backpack and it dumped out in my backpack. There's just atoms in my backpack. So I stole this from someone else. Okay. So this water, for example, is actually tetrahedral. If you could see the 2 electrons clouds right here and here. So on this side, there's a lone pair, and on this side, there's a lone pair. So that's what I meant. That was you, right? Okay, so the electron domain would be called tetrahedral, but the shape is bent because you can't see the electron domain. But we don't usually talk about electron domain versus shape a ton in organic chemistry. The only way that ever comes up is when we draw molecules, we draw them in the molecular shape usually, and we put the electrons where they go. So like you'll see that I very rarely, I do this with alcohol, so I guess I shouldn't say I do this very rarely, but with water, I always draw it like this because that's its shape. Or the same thing with, well, there's not a lone pair around this, but with nitrogen, a lot of times it'll be drawn like this. And that's, you know, with the carbon-carbon triple bond, there's no lone pairs, but we draw it linearly because we like to draw molecules in the shape that they actually are in organic chemistry. But I don't usually count off if you make those mistakes where your shape is wrong, because I'm more worried about you knowing about the movement of electrons. And in my experience, the shape sort of comes as you practice visualizing the molecule. So early on, I don't worry a lot about it, but as we go through, I will, I'll always write that correction usually on your exam, like, hey, remember linear shape or, you know, whatever, but I usually don't count off on that, especially in ochem 1, but I want you to practice visualizing the molecule when you can. Yes. Okay, what else have we learned? Yeah. We learned functional groups. That was chapter 2. What functional groups did you learn? I screwed myself over by drawing my bonds here. What can you do? Functional groups, that's all we've learned in chapter 2, basically. And what functional groups did we learn? Alcohols. And how can you tell if an alcohol is primary, secondary, or tertiary? I think I heard someone say the number of carbons the carbon it's attached to is attached to, which is a weird way of doing it. But if you only looked at the number of carbons it was attached to, it would always be 1. So that's why instead of looking at this, we look at what this is attached to. And then what else do we assign primary, secondary, tertiary to? Halides and amines. I heard both of them. So halides, you do the same thing because halides typically only form 1 bond. So you have to look at what it's bonded to be able to tell primary, secondary, tertiary. Amines are different. You look at how many carbons they're bonded to. So like this would be 1, 2, 3. It'd also be positively charged. So that would be tertiary. if it's bonded to 2, secondary, if it's bonded to 1, primary. So amines are the one that's different, and they're the one that people usually get confused on. On the first exam, they're fine, and then the final comes, and they're like, "Oh crap! I was trying to see how many carbons the amine was bonded to that it was bonded to," and then they get confused. So try to remember that one's different. What other functional groups did we learn? Ketones. I thought I heard one that started with an E too. What'd you say? Ether? Ethers, yes. So ketones look like this, and they have a carbon chain on each side. That's usually denoted by an R. Another one is ethers. They have carbon chains on either side with an oxygen in the middle. So here's another one where I don't draw the right shape, but technically it should be more like this. But people don't usually draw it like that. What else? I heard esters and aldehydes. Aldehydes are so much like ketones, and they have similar reactivity to ketones. But one of them is what instead of a carbon chain? A hydrogen, that's right. And what is this carbon-oxygen double bond sometimes called? Carbonyl. That one you'll hear me refer to a lot, but it's not technically a functional group, that you need to know. Okay, and then I heard something besides aldehydes. What was it? Esters, I think. Esters are also kind of like aldehydes and ketones, except they can have H or carbon right there, but I'm just going to denote it as an R. And sometimes, to remember the difference between ether and ester. So Esther is a girl's name. I have a friend named Esther. She's the best. People will say, Esther likes spores. I spelled that wrong. Esther has an H in it. Wait, no, that's the girl's name that has the H in it. I always get that wrong. Okay. Esther likes Coors. C-O-O-R. Because Coors is a beverage you can drink, right? And people drink beverages. Ether isn't a girl's name. Ether is like the atmosphere. The atmosphere can't drink beverages. So that's how you can remember the difference between esters and ethers. I use that all the time to this day. I have I get my words mixed up really easily. So I always say Esther likes Coors, Esther likes Coors, Esther likes Coors. That's how I remember which one I'm looking at. Okay, what else? Amides. Amides are another derivative of carboxylic acids. Oh, well, I'll just talk about carboxylic acids while we're there. Carboxylic acids. What is this carboxylic acid? Do you guys remember the everyday life application? Vinegar. It's vinegar. What did somebody else say? Carbonic acid. That's in sodas. We talked about that when we were talking about a resonance structure with CO2 minus. A good one. That's true too. So carboxylic acid is in vinegar. And then we also talked about amides, which is another derivative of carboxylic acid. Any other functional groups y'all can remember? So many. I just heard nitrile, that's CN with a triple bond before it. I heard phenyl and benzyl. Phenyl is a direct attach. Benzyl has a bend in it. What else? Yes, so those are, I don't know if those are, sometimes they get classified as functional groups and sometimes they just get classified as like the backbone of the molecule. It's not super clear, but I do sort of classify it as a functional group. So there's alkenes, and what does alkene mean? There's a double bond in it, and what's alkyne? Triple bond in it, and what's if there's none at all? What is that called? Alkane, that's right. Okay, any other functional groups? You said methyl groups, I'm going to broaden that. So we learned about something called alkyl groups, which is when you have one of these as a substituent, you change the suffix to, or is it called suffix if it comes at the end? Yeah, to YL. I'm not going to make you know those until we get into nomenclature, and then you'll have to know all those names and identify when a functional group is a carbon chain, but you don't have to do that yet. I want you to start recognizing these shapes. What else did somebody else say? Alkyl halides on there? Yeah. Both of these are correct. So this just doesn't have the carbon chain on it, but R just denotes any carbon chain. So it could be like, and sometimes it can even actually be, I can't believe I didn't bring printer paper. Sometimes it can even actually be like a long carbon chain and then another long carbon chain. Sometimes it'll just be this. Sometimes it'll be in a ring. Sometimes it would be an H here. All those are correct. R just kind of means like any carbon chain. It's kind of just like a bloop. We put an R there to mean that it could be the same. So, and I have actually a TikTok video about that, but basically functional groups have the same reactivity, kind of no matter what carbon chain they're attached to. So that's why we put the R there, so you know that no matter what, this functional group is going to act the same, no matter what it's attached to, as long as it's like basically a carbon chain, or it could be a hydrogen unless like there's a specific other functional group that has a hydrogen, like the difference between aldehyde and a ketone. Okay, I think that's everything. I think that's all your functional groups. So this one we just did, this is a study technique. So you can do this by yourself if you have absolutely no materials. You can say, what have I learned in this class so far? And then you can just start thinking, or if you're in line at the grocery store, you can start writing notes on your phone. You can make your roommate listen to you. I had a student who would teach her parents what she learned every day in class. You recalling information about what we've learned is a study technique. And making a chart that has like the big ideas that you need to learn is also a study technique. And that's part of what I want you to get out of this summer class is I can't teach you everything I want to teach you in this class. I'm so sad about it because I love spending time with my students, but you guys have to be independent and be able to solidify this information in your mind. So I'm teaching you how to study on top of teaching you organic chemistry this summer. That is my goal for you. And oftentimes what students remember after this class is how to study, not organic chemistry. But once you have those tools, you can relearn it for yourself much, much easier, right? For when you're studying for your MCAT or for biochem or whatever. You had a question? A ketone has carbon chains, no oxygens, and an ester has to have that oxygen there. So I kind of think of actually this group as like stepwise increasing. So it's like the very simplest aldehyde is a formaldehyde. It has 2 hydrogens, and then it goes to an aldehyde with a carbon on one side, any carbon chain, and a hydrogen on the other. Both of those are aldehydes. And then a ketone has a carbon chain on both sides. And then a carboxylic acid has an oxygen and then a hydrogen. And then an ester has an oxygen and then an R group. And then a amide has an amine. So I like rank them out like this. And actually these are much more reactive than these. So ranking it out this way is actually also helpful because you start to learn like this positive center is a lot more positive than this one, which we'll talk about later. He has a question and then you, yes. Oh, the only difference between ether and ester. So this is ester. Ethers are things that smell and they don't have any carbonyl group. They just have an oxygen between 2 carbon chains. So this one comes up a lot. This is called diethyl ether. You'll probably use it in your ochem lab. But any carbon chain with an oxygen in the middle of it, but no hydrogen, like not an alcohol, it's just an oxygen stuck in the middle of a carbon chain, that's an ether. So ether looks like this. Ester likes coarse, and that's how I remember. Coarse has 2 O's, so do esters. Okay. Yes.
The Harvard, can an oxygen be in his bond, or is it just
No.
carbon?
You can never have an oxygen in place of the R group because that usually changes the functional group, right? Like in this one, there's an R group or there's an O where that R group is, that becomes a carboxylic acid. So R means carbons, sometimes hydrogens, if it doesn't change the functional group for it to be a hydrogen. It's just like a placeholder.
And then for the carbonyl group, when there's not anything attached to the bottom, there's that.
Like this.
Yes.
What does that mean? That's a carbon, because this is bond line formula. That and this?
Yeah.
Nothing. This is a specific ketone. It's technically acetone, like nail polish remover. And this is a general recognition that if you have a carbonyl between two carbon groups, it's going to have a specific type of functionality, and that's why we call it a functional group. Which two interchangeably?
Carbonyl and
Ketone. Carbonyl is this part of the ketone. So this right here, all these have a carbonyl. This is a great conversation because I love knowing what y'all's questions are. This is a carbonyl. So all these have this carbonyl in it. They're all sort of like classes of what they call carbonyl compounds, but they're different functional groups. They all have different functionalities in nature. So if you have a ketone, that's gonna act more like acetone will. It's gonna react with the same types of things. Ketones act similarly in nature. Amines act similarly in nature. There's a whole class of neurotransmitters called monoamines that end with an NH2 here at the end. And there's different R groups. Sometimes there's an R group here, sometimes there's an R group here. And they all can act as neurotransmitters like dopamine, amphetamine, and methamphetamine. Dopamine is what your brain naturally makes. Amphetamine is Adderall, and methamphetamine is meth. So dopamine keeps you going if you have proper executive function. Amphetamine, Adderall, will stimulate the production of more of that because it tricks your brain into thinking it has that. And then amphetamine does that to an extent that's too much, and then people are addicted, and it's really, really not safe. So all of those have very similar functionalities, right? But they all have different R groups on them. So that's what functional groups are, is they just act the same in all these different settings. Now the R group does matter, like methanol, ethanol, and isopropyl alcohol are all alcohols, right? And they're actually all poison. But if you drink methanol, you'll go blind and you'll probably die. And if you drink ethanol, you will just get a nice buzz, and then your body will purge it. Or if you drink a lot of it, you'll get hungover, or if you drink even more, you get alcohol poisoning and you could die, but it takes so much. So they're all poisonous. You don't want to ingest any of them, but one will make you go blind and the other will give you a buzz. And then isopropyl alcohol, I don't think is as dangerous to ingest, but it's still not great to ingest. So that's kind of what functional groups are, is they are the thing that's acting. And then there's an R group that is interchangeable, any carbon group, maybe even a hydrogen, but the thing that matters is the functional group will have similar reactivity. And the curriculum that you're going through now is what's known as functional group approach. So we learn functional groups, and then we learn how each of those functional groups react. So at the beginning, you're learning sort of the basics, and then it shifts pretty hard at ochem 2 into you'll have an aromatic ring chapter. You'll have a ketone chapter. You'll have an aldehyde chapter. You'll have a carboxylic acid chapter. You'll have an amine chapter. So that's functional groups are the foundation for what you're learning right now. So it's really important that you get the functional groups. There's another approach, I actually like it better, called mechanisms first approach, where they emphasize the mechanism and similar patterns that are found in the way the electrons move in different functional group reactions. And I try to incorporate some of that into your functional group approach as well. So like we'll learn substitution reactions, and there's substitution reactions on alkanes and ketones and you know, aromatic rings. And so I kind of group those together in my mind, but you learn them in different chapters. So I try to like draw connections between those as we go through the chapters, if that makes sense. Okay, was that helpful? I went down a rabbit hole, but that's actually good because I built in time for us to go down rabbit holes today because I was feeling like we were hurtling at a breakneck speed and I didn't like it. Okay, and so yes, this is a close overview of what we've gone over. It's not everything, but these are some of the biggest things I do want you to know. And then obviously I also want you to know bond line formula. And actually I think the rest of chapter 2 is more review. Raise your hand if you know what intermolecular forces are. Hell yeah. Okay, so we can go through this kind of quick, and we might have time at the end even to do some resonance practice. Do you guys want to do resonance practice? Yeah, that's kind of what I thought. Okay, so let's talk about intermolecular forces. Somebody suggested in the survey that they want like a 30-second overview of what we're going to learn before we learn it. So I'm going to do that. I thought that was actually a really, really good idea. We're going to learn about intermolecular forces. There's 3 kinds of intermolecular forces. So far, we've learned about bonding, and we know the different types of bonding inside of one molecule. Like if in water, how an oxygen is bonded to a hydrogen, it's the overlap of orbitals. It can be covalent, they can be polar, they can be ionic. Okay, well then those molecules in real life are not isolated by themselves. They're interacting with other molecules. And intermolecular forces are basically the foundation for absolutely everything that happens in your life. They're the reason that honey is sticky. They're the reason that geckos can walk on walls. There's the reason that water has surface tension and is liquid at room temperature. There are so many episodes of Chemistry for Your Life that we've done where I'm like, the return of intermolecular forces, to the point that we made a joke shirt that says, may the intermolecular forces be with you. Like, they're everywhere, they're around. So that's what we're going to do today, is we're going to talk about the 3 major kinds of intermolecular forces, and then how they impact, how the structure and the intermolecular forces impact the function of things in the world. So that's mostly boiling point, melting point, and then also solubilities. Those are the big things. So that's the 30-second overview of what we're going to do today. We're going to touch on IR spectrum, and that's it, because it's not really significant, and you'll get a better understanding of it if you work in a research group. And it's only a little bit on the ACS exam. I don't actually think it's on the MCAT at all. But we do have chapter 9 at the end for NMR, and I will bring IR back at that time. I'm basically just going to tell you what IR is so you don't look silly when you leave here with a science degree and you've never heard of IR before. Okay. You have no idea how much talking dries out your mouth. It's crazy. Okay, covalent bonds. Those are the type that we talk about most often in organic chemistry. We don't have a lot of ionic bonds that we look at, except for if something is negatively charged. A lot of times you'll see a positively charged, what's called a counter ion. So like if you have OH minus, you might see K plus. Before, that's always been considered KOH for you. But in organic chemistry, we basically ignore counter ions. We do not care about them. They exist, and as soon as I see it on my paper, I'm like, bye, we're just doing negative charges. I don't care anymore. So if you see something like a K or an Na or an Li, that basically means that's positively charged and the thing it's next to is negatively charged. And that's the extent of ionic bonding we deal with. Otherwise, we deal with covalent bonds, and covalent bonds are on a spectrum. Actually, all bonds are on a spectrum, but covalent bonds are either shared perfectly or they're playing tug of war. And that's the best analogy I can think. When they're shared equally, the electrons are spread all around the orbitals, the hybridized orbitals, or for the hydrogen orbitals, the s orbitals, equally. And there's not a higher area of electron density on one side or the other unless something comes near it that makes the electrons move. If you have a polar covalent bond, they will not be equally shared. So one thing will be more electronegative, and it's going to pull all the electron density towards it, and it'll have a positive side and a negative side. So this is still about bonding within molecules, but we have to know about bonding within molecules to know how molecules then interact with each other. Okay, and then different electronegativities are literally arbitrary. I think this is hilarious. I mean, they're not like literally arbitrary. They experimentally determined which ones are stronger and which ones are less strong. And then they just decided that the strongest one was 4. So fluorine is the strongest one, but that number doesn't really mean anything except to be able to tell the difference in electronegativities between the two. It's just an arbitrary scale. So I don't want you to know those numbers, and I don't expect you to use those numbers. I do expect you to know that fluorine, oxygen, and nitrogen are some of the most electronegative, along with chlorine and bromine. And knowing the electronegativity trend pointing towards that fluorine is helpful. But I don't expect you to know the numbers of electronegativity. They're just arbitrary anyway, so who cares? Not me. That's the difference between me and an analytical chemist. They'd probably like die if they heard me saying that. They're like, numbers are everything. And I'm like, it's fine, just whatever. And here's kind of an example of how those electronegativities are used. So they would subtract one from the other to calculate the dipole moment, basically. Ionic bonds have a very intense dipole moment that we essentially have decided means that they might as well just be separate, and this one's positive and this one's negative, and they're just like near each other. Whereas on the other end of the spectrum is equally shared bond. Yes, also wait, before you answer your question, when I stand right here, you're behind this. So if I'm not answering you, it's not because I don't like you, it's probably because I don't see your hand. And you're like the only person that's blocked when I'm standing right in my space, so I just want to warn you. Oh,
Yeah.
that's kind of sad. Well, I talk with my hands anyway, so it's fine.
I was just gonna ask if we have like a little bit of time to do one practice problem of like calculating the dipole moment, because I know it's not.
No. And here's why. Because I want you to understand how to calculate dipole moment, but you'll never do it on a quiz or a test. So I would way rather you know what dipole moments are and us do different kinds of practice problems, and you just do that one on your homework so that you know what they're for and never think about it again. That's what I want. So I'm going to say no on that because I only want to do practice problems in class for things that are very valuable for our time. But that was a good question so that I could communicate that. Some things have absolutely no dipole moment. Those would be considered non-polar. Okay. Now, another thing we have to talk about, and this sometimes confuses students, so I really want you to dig in with me here. We've talked about bonds within molecules, and you can have polar bonds and a non-polar molecule. So polar bonds are different than polar molecules. You can have 4 polar bonds that are all going in opposite directions. The pull will be equal, and the overall molecule is not polar. Okay, great. And you can have all non-polar bonds, but with one lone pair, and the overall molecule will be polar. So polar bonds, polar molecules, not the same thing. Okay, so this is a good example. Well, the carbon-hydrogen bonds are really close. They're slightly polarized towards the carbon. Most of the time they're in the tetrahedral arrangement, so they're all pulling in opposite directions. So hydrocarbons are usually non-polar. But that chlorine's really polar, so it's pulling up. So all these are polar bonds, these slightly less, this slightly more. Notice the arrows are pointing in the direction that the electrons are going. That's a trend in ochem. Always electrons pointing in the direction they're going. And then one side will be more negative of the overall molecule and one side will be more positive. So this molecule has polar bonds and the molecule is polar, both. When we're talking about intermolecular forces, we care about the overall molecule's polarity, not necessarily the individual bonds polarity. Okay. Here's an example of one that this mu, I think that's called mu, means the overall dipole moment. So the overall dipole moment on this one is 0, even though there are 3 very polar bonds between boron and fluorine. Fluorine loves to pull electron towards itself. That boron is going to be very positive, and somehow still this overall molecule is neutral because they're pulling it all in the exact opposite directions of each other. So it cancels out. So this is a little bit of vector math. You don't actually have to do the vector math, but you have to be able to look at it and know if they're canceling out or not. So there will be, at least in your recitation, probably as a free response question on your exam, because I didn't get to do it on a quiz, a molecule with, just like what you had on the quiz, the example, the question 4 that I was like, I'm taking this off. It'll have either polar or non-polar bonds, and then you'll have to say for each bond if it's polar or not. And then you'll have to say, on this overall molecule, is this polar or not? You'll very likely have to do that. Okay, and then here's another example of the same thing, tetrahedral, they all pull in the same direction. So I usually try to think of this in terms of symmetry, like, do they feel like they're all pulling in the same area equally? Yes. So that means they all have to be the same atom, like all those are fluorines, all those are chlorines. There's two, or like one fluorine and three fluorines, they would be pulling differently. So it has to be the same atom, there has to be symmetry. You'll kind of start to recognize it as you go through, but I'd rather you spend time practicing this than like doing the math. That's kind of what I meant. Someone raise their hand over here. Yes.
So is the molecule or polar or not?
Both of these molecules are not polar, even though they both have polar bonds. It's just like the tug of war. Like if two people are pulling really hard, exactly the same amount in opposite directions, that flag in the middle is not going to go either way.
Are they covalent?
They're polar covalent. Yes. So all those individual bonds are polar covalent bonds, but they cancel each other out as they're pulling the electron density away. And because of that, the overall molecules. Yes. Mhm. A non-polar. Say that one, just the last part. I just at the beginning, which is great. There's such a thing as a non-polar covalent molecule. Like, do you mean the individual bonds are all not polar, but the overall molecule is polar? Or do you mean the individual bonds are not polar and the overall molecule is also not polar?
Oh, I'm trying to think of the first example.
Right. I think a non-polar covalent molecule would just be if all the bonds are non-polar, everything's equally shared all around. Like hydrocarbons are considered overall non-polar because that tetrahedral shape, the hydrogens or carbons are all pulling off in the same direction, so overall it's non-polar. Or like hydrogen molecules shared equally together, that's a non-polar molecule. It's also only made up of one non-polar bond. So those would be examples of that. Does that answer your question? Sorry, I came over here and told you I didn't want to make you shout. And also I like to sometimes leave behind my desk and it's like, I'm on y'all's side. I really want you to succeed. Okay. So dipole moments in alkenes, this kind of goes along with like when will they be able to cancel each other out. We talked about cis, trans, isomerism. That was one thing we covered at the beginning of class. So we didn't get to that in our outline because we went down a rabbit hole, but we did talk about isomerism. Cis, trans, isomerism, part of the reason they have different properties is because the overall molecule will have different polarities. So this molecule, those two chlorines are pulling down on the same side of the molecule. So these two polar bonds are adding up, not canceling out. So the overall molecule is polar. But for trans, these are pulling in opposite directions. So the overall molecule, even though it has the same two polar bonds, because they're in different places, non-polar. So isomers don't always have the same properties, even though they seem like they would because they have the same condensed structure or the same condensed formula, and their only difference is that they're arranged differently in space, but they can have very different melting points, boiling points, etc., because their individual bonds might not be pulling in the same direction. So one of these is polar and one of these is not. Did I miss anything on that? No. Okay. So now let's talk about intermolecular forces. So if you have, there's three intermolecular forces. London dispersion, they're everywhere. You guys have learned about these a lot, I think. I learned about them in high school and then again in Gen Chem and then again in OChem. So I'm going to go pretty quick. London dispersion forces are if you have two non-polar molecules and they come near each other, electrons repulse just like magnets. So if you, because they're both negative, so if you bring a negative towards another negative, this negative is going to be like, nope. And there will be what's known as an induced temporary dipole. And a way that you can see that in nature is actually lightning. So in lightning, there will be a collection of electrons at the bottom of a cloud, and it will pull positive charges or push away negative charges. And then the connection between the bottom of the cloud and the positive charges on the Earth makes a channel for electrons to travel, and you literally are watching the energy in lightning, you're watching the energy of electrons move, just go flash, flash, flash. That's literally electrons traveling. All electricity is electrons traveling, really. But I think lightning is especially cool. So, yeah, that's a temporary dipole. When two things that are roughly equal come near each other, they will sort of shift to where there's more electrons on this side, more positive charge here, more electrons on this side, more positive charge here, and then they can kind of temporarily hang out together. And it's known as a temporary induced dipole because as soon as they come back apart, they'll kind of even themselves out again. Okay, that is responsible for why geckos can walk on walls also. It's the weakest intermolecular force, but geckos, their little feet have so much surface area that all of the collective surface area with all of the collective molecules on the outside of their feet add up to a strong intermolecular force, even though it's like it's just a whole lot of the weakest intermolecular force. Isn't that weird? I love it. Okay, there's an episode of Ologies about that like sort of goes into it. It was really cool. So yes, intermolecular forces, the forces that act between molecules. Dipole is when two molecules that already have a dipole in them come close to each other. So if you have like a carbon bonded to an oxygen, like we've seen this ketone structure quite a bit, and those two come near each other, naturally the positive charge is going to hang out near the negative charge. So we've learned so far in this class that there's electronegativity in this molecule, so that leaves a partial positive right here. And we've also learned that there's resonance in this molecule. So both of those things, this resonance effect and this inductive effect together mean that this center is pretty positive. And so this molecule, if I were to sort of draw the shape of it out, sort of like that, it's trigonal planar, and I'm going to try to draw electron density, and I'm not very good at it, but the PowerPoint will be better. How's it already 12:29? The negative portion would be on one side. This one's kind of neutral. And the positive portion would be on the other side. And so the negative portion and the positive portion will have an attractive force between them. Another example is, I'm trying not to use anything with texture. Okay, I'll do HI. So iodine is more electronegative than hydrogen. So this side will be positive. This side will be more negative. So this is like higher electron density over here. And then if you had the same type of molecule, where this side is more negative, and this side is more positive, they'll line up like this, and there's an attractive force here between the positives and the negatives. Okay, and then hydrogen bonding is not bonding, and it pisses me off that they call it that, because it's one of the biggest misconceptions in all of chemistry, but my students aren't going to have that misconception, okay? Hydrogen bonding is what? Say it with me. Not bonding. Hydrogen bonding is what? That's right, thank you. Hydrogen bonding is an intermolecular force. And what I like to think of hydrogen bonding as a super dipole. So hydrogen bonding only happens, it happens between molecules. There is not a bond. But if a hydrogen is bonded to a fluorine, an oxygen, or a nitrogen, that dipole is so significant because fluorine is so electronegative and hydrogen is so willing to lose its electrons, it only has one to begin with, that it is so positive on one side and so negative on the other side that the connection that forms here is stronger than any other molecular force and it's bridging on becoming to the strength of a weak covalent bond. So that's why they call it hydrogen bonding. It kind of pisses me off. So if you have hydrogen bonded to fluorine, there's a high electron density here, almost no electron densities there. And then same thing again, low electron density, high electron density. This is so positive, this is so negative, that these portions together, their attractive effect is so strong that it will almost act like a bond. And that is why things like water are liquids at room temperature, because they're very small molecules. So in theory, you should be able to break them apart and turn them into gas pretty easily. But because in water you have a bond between a hydrogen and oxygen, this side is so negative and this side is so positive that they will bind near each other so strongly on this hydrogen bonding intermolecular force that it is very hard to break two water molecules apart. And that's also why there's things like water bugs who can walk on top of water, because water's holding so strongly to itself that some light creatures walking on it does not break those intermolecular forces. Okay, yes.
I was just gonna ask if that was the
Yes, it is. Yeah. And you'll even see if there's like, you know, the bottom of the meniscus or whatever, or the top of the meniscus. The reason that water can shape like a dome when it's in something is because it's holding tighter to itself than it is to the glass. So it's like, that's why water makes a shape sometimes, like holding on tight to itself. So intermolecular forces are the foundation for everything in everyday life, and they aren't though as much in organic chemistry. In organic chemistry, we actually watch molecules move, but it's important that you understand that the overall molecules are polar and how they interact. But we'll actually move electrons more, but you need to know where those high and low electron densities are and what's going to come near each other in a solution as we go through organic chemistry. Okay. So we already talked about dipole-dipole forces. That's the attraction between these two because there's a partial positive and a partial negative. I'm going to go quickly because you've had this many times before. Again, that's dipole-dipole. Now let's go to hydrogen. Hydrogen bonds are not bonds. That pisses me off. It's not a bond. It's an intermolecular force. It's a very, very strong intermolecular force. It's basically just super dipole. So, and if a hydrogen is available for hydrogen bonding is what we'll call it, is when that hydrogen is bonded to oxygen, fluorine, or nitrogen. So the bond between the hydrogen and the oxygen, the hydrogen, the nitrogen, hydrogen, fluorine, that's not the hydrogen bond. The hydrogen bond is the intermolecular force between the two molecules. Ugh, I hate that I have to explain it. I'm like, why can't we just call it hydrogen intermolecular forces or super dipole-dipole? I don't get it. But my chemistry teacher helped me remember which molecules that goes with by saying H with fun, sort of like fun. So I just remember that, F-O-N. So they're not bonds, they're super dipole, they're weaker than covalent bonds, so stronger than other intermolecular forces. Hydrogen bonded with fluorine, oxygen, and nitrogen. This explains boiling point, so why water has a much higher boiling point than methane, and why water is liquid at room temperature. And surface tension, you can do that thing, it's really cool. If you put a paper towel under a paper clip, and then you take the paper towel out, the paper clip will keep floating on top. It's amazing. And it's because of intermolecular forces. Okay, so that's an overview of all the intermolecular forces. Oh, we didn't do dispersion. I did that first. I did it backwards. So this is kind of an idea of the induced dipole is when they come near each other. See how the positive charges line up on one side and the negative on the other? Because negative charges don't really want to be by other negative charges. So these positive charges are pulling the negative charges towards them. But if they were separate, it would be nonpolar and the negative charges would be equally spread around. Stronger dispersion forces come with increased polarizability and more surface area. You really won't be tested on that except for maybe some boiling point questions, but usually those focus on other things. Okay, so these things impact function, not only water at room temperature, but also why things act the way they do. So ionic bonds, their intermolecular forces are a little different. They do what's called a lattice structure. And the way I think of this is like if you've ever seen a building being worked on with construction, and there's like those scaffolds, right? Where it's like just like a big grid with like repeating units, and then people can walk around in them. If you like shrink down to the molecular level, that's kind of what an ionic molecule looks like actually. Because instead of it just being like a sodium chloride, there's a sodium surrounded by chlorides, surrounded by sodiums, surrounded by chlorides. So we call that a lattice structure. And those are basically the whole structure is kind of involved in the ionic bond. They're just all drawn near each other because of the positives and negatives. And those are so strong, I see you. Those are so strong that instead of them melting, a lot of times ionic solids just degrade because the bonds are breaking before you can break the intermolecular forces, because the intermolecular forces and the bonds are almost indistinguishable. Yes. It's kind of different. I bet I can look up lattice structure on the internet and show you. Let's see if I can get something here. Oh, a phrase. This is what lattice structures look like, and they're held so strongly in there because of the positive and negative, right? So like this sodium in the middle is surrounded by chlorines, and that chlorine has, each of those chlorines has a sodium around it, and each of those sodiums has a chlorine around it. And so they make those really crystalline structures. Like if you see like they have like NaCl prisms, like literally just like salt prisms that are like so beautiful. And it's because they've crystallized in this very strong lattice structure. So you can kind of see, it's like, where does the bond end and the intermolecular force begin? In inorganic compounds, it's almost like there's no difference. But that is inorganic chemistry, not organic chemistry. So you don't have to worry too much about it. But that's why like salt doesn't really melt. It just, like most salts just kind of like start to degrade. They just like break down. They don't ever have a melting point and a boiling point. They just kind of like destroy. Some of them will melt, but most of them don't boil. Okay, and when they dissolve, they're not melting. All that happens when you dissolve a salt is you're separating out those positive and negative charges. So that's a way that you can sort of break up the intermolecular forces, but you're breaking up all of them. And then they're just all moving around in like water, for example. This outside of the scope. So I'm going to go back over here. Okay. So you need a lot of energy to break up that lattice, but the induced dipole, it's not permanent. That's the difference. So it's like that's permanent. This one, they come near each other, they have charge, they hang out, and they move on. It's almost like a blind date or something. They come near each other and they're like gonna be pleasant, and then they're gonna go their separate ways and never see each other again. I don't know. Some blind dates they pair off forever, but that's not how bonds work. So that's kind of the idea. It's like they come together, they move on, and that's it. Oh, a bridesmaid party. That's a great example. Bridesmaid parties. I don't know if you guys have been in weddings, but you like rally around your friend. A lot of you have never met before, and you're like, we're best friends. And then you're like, okay, I'm never gonna talk to these girls again until she has a baby. Like that's what induced dipole is. Like for a moment you're bonded, and then you're like, or I guess not bonded. For a moment you're intermolecular forced together, and then you're like, I'm done, and that's it. So that's a perfect example of a dispersion. Oh, that's a good one. I wish I had had that in my brain before this moment. Okay, so water boils when vapor pressure equals atmospheric pressure. So what water boiling is those molecules are starting to separate out, and instead of being close together, they separate out and go into the universe. So when the pressure that's like those gas molecules on top of the water meets atmospheric pressure, the gas molecule or the water molecules are free to turn into a gas. So they go from liquid to gas. They just have enough energy to spread out from each other. But because it's dependent on atmospheric pressure, boiling points actually are different at different pressures. So if you try to boil a pot of water at the bottom of the ocean, somehow, if you could like get a bubble and a heating thing, there'd be so much pressure that it would take for freaking ever for that to boil. But if you go to the top of Mount Everest, you'll boil it really quickly because there's almost no atmospheric pressure. But the water boiling at the top of Mount Everest is not going to be at 212 degrees Fahrenheit or 100 degrees Celsius, it's going to be at like, I think it's like 90 Celsius, maybe. It's like lower. And the water boiling at the bottom of the ocean is going to be like 3,000 degrees or something crazy. So it'll get to the right temperature that you need to cook foods, but it might just not do that boiling effect. So boiling and temperature are not constantly related. It's more about the pressure. And again, you have to overcome the intermolecular forces that are holding it together as a liquid so that it can spread out and turn into a gas. So all you're doing when you go from a solid to a liquid to a gas is you're breaking up intermolecular forces that are tight to making them less tight to making them free to roam around at will. That's like what going from a solid to a liquid to a gas is. Okay, and so that's why intermolecular forces can impact melting points and boiling points. So more dipole, this down here, sodium acetate, see how I said, remember I said if there's a sodium, a K or a lithium, it will just basically be a counterion and I don't care about it very much. That's what this is. So this sodium is positive, this is negative. So this is actually more like a salt than having a bond. So it can melt, probably because of those carbons, but it never boils, it just degrades, just like goes, it like turns into carbon and nitrogen broken down, gets black. But these other ones will boil and they'll also melt. And you can see this is a nonpolar molecule. So what intermolecular forces would exist between two of these? Only London dispersion. So they don't have any built-in dipole. The only dipole that exists is if they come close to someone else like them and the negatives repulse each other and they're temporarily bridesmaids together. So it's easy to break it up. So that's why it's very hard to get into a solid, and it is even a gas well below room temperature. Now acetaldehyde, let's do one. So CHO, do you guys remember what functional group that's for? There's a hint in the name. It's an aldehyde. CHO is the shorthand for aldehyde. And in one of my videos yesterday, I kind of went over why, I think the recitation video, and how you know that. But CHO is an aldehyde, so there is some hydrogen bonding between the hydrogen, well, I guess not. Alcohol would be a better example, but they don't have one on here for me. There's hydrogen bonding in acetic acid because it's a carboxylic acid. So there's a hydrogen bonded to an oxygen. So that's really polar. So the hydrogen on the carboxylic acid is very positive. That's also why it's called an acid, because it's very positive. And then the oxygens are pretty negative. So that positive charge can come near the negatives and they'll be held tightly. Now, in this case, actually, the hydrogen bonding is not as strong as it would be if it was an alcohol. Can you guys think of why that might be? I'm going to draw it for you. That could have been really bad. Yes, who said that? I love it when people answer resonance. Okay, so this OH has a resonance structure. Where, you have a stronger negative here, but it's sort of dispersed around with this positive charge. So this hydrogen's not going to stay as positive. Whereas if you have alcohol, it gets all the lone pairs all the time. So this hydrogen could bond more easily with it. So the resonance spreading out that negative charge actually detracts from the hydrogen bonding in this case. But it benefits in some other cases. And we'll talk about that a lot in chapter 3. Way to connect those dots. That made me really happy. That shows me that you're actually understanding and thinking and not just memorizing to get your way through this class, which is my dream. Okay. I don't think I'm sad we always miss our practice problem breaks, but we're going to miss it again because we have less time. Again, you can see the dipole, the permanent dipole in the cis isomer makes it to where it has a higher boiling point, so it's harder to break apart. And in the trans, it's easier to break apart. Now for solubility, typically we say like dissolves like. So things that are very polar will dissolve other things that are very polar. You've seen this in life all the time. You can mix alcohol and water. Can you mix water and oil? No. Why is that? Oil is nonpolar. Do you know what oil is made up of? Hydrocarbons, baby. So hydrocarbons, not polar. Basically, vegetable oil, margarine, butter, all of those things are hydrocarbons and they're not polar. They're just different forms of hydrocarbons, which is why some are liquid at room temperature and some are solid. Better or worse intermolecular forces. And they will never interact with water because water is very, very polar. It has super dipole. It's hydrogen bonding intermolecular forces. And all that oil has is induced dipole. And so it just really can't hang with the water. Is way more attracted to itself than it is to the other party. But alcohol can mix in water because it also has hydrogens available for hydrogen intermolecular forces. So alcohol can hang with water. Alcohol and water do have some level of attraction. Okay, so polar and ionic solids are usually soluble in polar solvents. That's also why salt dissolves in water. Even though water isn't technically an ionic liquid, it has such a strong dipole moment that it's able to surround those positive and negative charges, and it can break up the lattice of salts. Polar liquids are usually miscible. That means they mix in with each other. So solids going into water is usually called solvents and dissolving. Liquids mixing with each other is called miscible, which to me sounds like mixable, so that's how I remember it. And then non-polar solvents usually will dissolve in non-polar solvents. So that's why if you eat a pepper, you want to drink milk because there are fats that are non-polar in the milk. And the thing that hurts in capsaicin in jalapenos is capsaicin, which is also a non-polar organic molecule. If you drink water, it might move those capsaicin molecules around, but that's just going to spread the pain. It's not going to take them away at all. And then non-polar liquids are usually miscible with each other, so different types of oils and stuff like that can go together. And then polar and non-polar liquids like oil and water are not soluble to a large extent. And we've talked about where that plays out in everyday life. So this is just some kind of examples of that. Hydrophobic is when things are non-polar. So this part of this molecule is hydrophobic. If it likes water, it's hydrophilic. So if it's polar, it's hydrophilic because it likes water. If it's non-polar, it doesn't like water, so it's afraid of water, so hydrophobic. So that's just basically another way of saying polar and non-polar. Many soaps and detergents have a strongly polar end, so they can interact with water, and a strongly non-polar end, so they can interact with oil and dirt. So they'll surround the oil and dirt with their non-polar end, and they make what's called a micelle. And so that means it's just like a ball on the outside of all the polar parts. It kind of looks like sperm in pictures, which is icky, but if you can imagine that. Like sperm tails pointing on the inside and a bunch of sperm heads on the outside, that's I know it's gross, but everyone is picturing it, right? And that's the part that's polar, and the polar part can interact with the water and then be washed away. So that's like basically what a micelle is. It's the grossest analogy, but okay. There's a picture on one of the organic chemistry books. I think it's Solomon's chapter 11 that I'm like, this just looks like a sperm on the canvas. But like, what? Did they not get what that looks like? Okay, whatever. That's okay. We're all going to be medical professionals or PhDs of some sort here. Okay, structure, impact, function, solubility. So usually organic compounds are not soluble in water because they're primarily carbon-based. If it has a solubility of 3 grams of this molecule can dissolve in 100 milliliters of water. Class is over, but I'm going to try to finish up chapter 2 really quick. You can watch the last bit of video just so that you're all ready for to do your homework. Compounds with 1 to 3 carbon atoms usually are where that stops. If you have more than 3, it's usually 3 grams won't go into 100 milliliters of water. And just for reference, this is 100 milliliters of water, and 3 grams is like a tiny pinch of salt, roughly. Okay, and then all infrared spectroscopy is a spectroscopy that lets us look at functional groups. So if you shine infrared light onto a molecule, the molecule will move. And based on the movements of the molecule, the infrared spectroscopy can pick up on that. And it gives different signals for different functional groups. So if I make something in my organic chemistry lab and I want to prove that it has an aldehyde or a carboxylic acid, I can use an IR instrument to tell me if that functional group is present. And that's it. That's chapter 2. Thanks for letting me keep you for 2 extra minutes. I try hard to be respectful of everyone's time, but I really wanted to finish that. Okay, we'll dive into chapter 3 tomorrow. And then your exam will be whatever we cover for chapter 3. So please, please, please do practice problems for chapter 3. And I'm going to post videos ahead of time to prepare you to think about chapter 3. Okay. Probably will be, but tell me in person first. Yeah, will you email me that, remind me that your aunt passed away, and then tell me like roughly how long you want me to open it to? The thing is, I don't want you to not study to do your homework. So be studying. That's part of why I make it do Friday and not Sunday, is because I'm like, do your homework and then focus on whatever you're missing. So also study. I know that's shitty to have to study at a funeral, but also do your best to study. Okay, I'm gonna pack up while y'all are asking me questions because I gotta go record an episode of a podcast at 1:30 and it's already almost 1. Okay.
Would you do an offsite tomorrow after 4?